Good.
Yeah, it's perfect.
Perfect. So yeah, thank you very much, Karen, and very happy to be, well, ideally I would be there. I love Seattle so much as a city, but very happy to be joining and presenting remotely. So yeah, as Karen said, I'm going to be talking today about how I don't think I'm alone in thinking this, but how I see behavior prediction as really a nucleus and an origination point for much of modern AV research. And hopefully I can kind of interest you in either continuing some of those research lines or at least give you some more sense of what's going on in the field, especially as it relates to prediction. So yeah, I think you guys have, as I understand, spent the past few weeks talking about behavior prediction, talking about this problem of predicting what might happen in the future, and then thinking about how to use that in order to, at least in the cases I look at, for example, plan a trajectory for an autonomous vehicle. Doesn't have to be an autonomous vehicle. Could be a sidewalk robot, could be a collaborative robot, could be a in-home robot, lots of different applications. As you can imagine, I'm going to be talking a lot about autonomous vehicles today, but the core ideas generalize across multiple different applications. And I think you've also, I don't know if you've actually seen this exact figure, but I think Karen has told me that you guys have talked about some of the different classes of trajectory prediction methods that that exist and that have been published in the past few decades. Now, there has been, I can tell you, so I wrote like a blog post some years ago, which kind of tried to give a, an ontology here of different trajectory forecasting methods. That was back in 2020. Since then, there's been quite a few advancements in the field, and I would say particularly so in this use of deep learning generative models for trajectory prediction. I think you guys have talked about this in the course, but I can tell you from the research perspective, this particular subdirection of trajectory prediction has grown significantly since 2020, with literal hundreds of papers since then, maybe even 1,000 or more. It wouldn't be a stretch to think. And particularly what I'm going to talk about today, I'm going to first start from kind of, let's say, starting from maybe 2020, seeing what are the trends that have emerged in terms of models that are being applied today. Then I'll talk about how from behavior prediction, it kind of spurred a lot of research into end-to-end driving. And I'll talk about two different ways in which that's happened. And then I'll talk about actually applications beyond just the AV stack itself. And I'll talk about how, especially in simulation, behavior prediction has been a critical component of some of the latest advancements in that. And then I'll show some of the latest works in that space. So without further ado, let's get started looking at what are the actual approaches used today in practice within at least the autonomous driving field. So one easy way to take a look at this is just to take a look at the current leaderboard. This actually might be a year old. Yeah, I think this is from 2023. But one way you could do is look at the leaderboards of prediction challenges in your field of interest. So in autonomous driving, every year, Waymo typically hosts a set of autonomous driving challenges using their data set. They released a data set some years ago as well of autonomous driving data. And what you can see is all of these different methods. Well, I guess it might be hard to kind of identify them here, but like I can tell you, for example, this MGTR or MTR++ or GTR or whatever, all of these, like when you say TR, typically it's referring to the use of a transformer-based model. And you can see that these kinds of models are kind of towards always the tops of the leaderboards. And so it kind of gives you a clue that it looks like transformer-based models are basically the state of the art for trajectory prediction. So let's keep this in mind and look at another challenge from Waymo. So they have prediction challenges, they have perception challenges like object detection and stuff like this. And then they also have a simulation agents challenge. So basically, for the most realistic agents that you can come up with in simulation. And you can also see here, similarly, you see a lot of, T acronyms or former used in the name, which basically is hinting at the use of transformers as well. And kind of spoiler alert, I can tell you that exactly. Transformers have been the absolute, basically cornerstone of much of modern trajectory prediction research, at least architecturally. And I'm just showing here, I know there's like a lot of things going on in this slide, but I'm just showing here a sampling of some recent works, just from the past few years that all use transformers in different ways to do trajectory prediction. So on the top left here, I hope you can see my mouse, but basically on the top left here is the architecture diagram from Waveformer. This is a trajectory prediction model from Waymo from the past few years. On the right here is a model called Trajeglish. This is from NVIDIA, from a colleague of ours at NVIDIA. Also, this one actually might have been this year or maybe just towards the end of last year. And then on the bottom here, this is a little bit more complicated figure. This is MTR++, which is from a German university. And you can see here, okay, there's a lot going on here, but you can see kind of on the right, you see this transformer decoder and all this, which is kind of the core computation here. And I want to say, kind of stepping back more broadly, in the field in general, just like transformers kind of supplanted RNNs or, general sequence modeling tasks in basically all of NLP, they have also done so within behavior prediction. And it's really for the same reasons. So the reasons this happen in NLP are the same as they happen in autonomous driving behavior prediction, because they're more scalable. They have a much higher capacity than RNNs. And the parallelism of their architecture means that you can much more efficiently train them on the hardware that we have today. So you basically get a lot more bang for buck in terms of using them over kind of the architectures of yesteryear, which were RNNs predominant. Now, that's kind of let's call it the core architecture of computation. Now, there's also been a pretty big shift in terms of the input representation that researchers have used. So probably 4 or 5 years ago and behind, the vast majority of models were using CNNs in order to encode static, information like maps and then process them into features. Nowadays, we can see that basically everything is everything has switched to like a vector tokenization strategy, where basically every object or every map polyline is encoded individually and then processed within a transformer using attention. So I have a question here for the class. Can you all think of some reasons for why vectorized representations have largely replaced rasterized ones? I told you the reason for transformers, but I want you guys to figure out why are vectorized representations much better? And I don't know, Karen, if you need to like unmute the room or something like that for me to hear.
Yeah, we have a hand up. Do you want to scream?
Yeah, go for it.
Yeah, can you hear me?
Yeah, yell a bit louder and then we'll be good.
Okay, because rasterized inputs might be resolution dependent, and so like getting sparse trajectories is hard or could be hard through a CNN, and extracting those features might be difficult. So having vectorized inputs is potentially better, more efficient.
Yep, this is a great, and I'm going to rephrase a little bit your answer in that it's exactly, you might have in a rasterized image something like 98% of pixels completely useless, or you don't care about them, or they're off the road, or you're kind of wasting computation there. So exactly, efficiency is easily one of the most, I would say, probably the number one reason. Can anyone think of any other reasons?
Could it be like the self-attention mechanism? So it's like more contextual than CNNs, which are very adjacency kind of dependent.
Yeah, so actually, I would say this is it's kind of like I would maybe rephrase a little bit to just say you're able to more efficiently capture the connectivity of different components. Yes, so self-attention, cross-attention versus, something like exactly like you said, the spatial locality of when you're passing a filter over. Yep, I think that's another great reason, probably number 2 or 3 in the list. One more. Anyone have one more idea? All right. So you guys basically hit them all anyways. I would say the only other thing I would change, the only other thing I would add, sorry, is that, so at training time, everything you said, perfectly correct. Online, there's also a massive benefit to, typically the number of elements within a scene is not that large. Let's say at most, maybe you get something like at very dense, intersections or something like that. Maybe you might get 50 agents within view or 75 agents or something like that. And it turns out that's pretty small compared to if you have to process very high resolution images. So you actually even get a computational efficiency boost in terms of even with all the attention operation and everything, it just means that you have such a smaller amount of data that you have to work with. So yeah, great. So those are the reasons also why input representations have changed. And then finally, the actual problem factorization of trajectory prediction has also changed or kind of evolved since it used to be back, maybe 4 or 5 years ago. So before, everyone was doing something called marginal factorization of trajectory prediction, which means every agent's future was being predicted independently. You can probably imagine that this might give you some wonky scenarios because even if each agent is, let's say, very likely to just continue driving straight, if you're not accounting for the other agent doing that as well, you're going to get things like collisions being, marked as likely, which is not really feasible. And so now a lot of the times we see trajectory prediction works doing something called joint prediction, basically predicting for all agents' motions at the same time and actually accounting for that, these joint probabilities within internally in their models. So with all these, now bringing everyone up to the state of the art, let's look at some ways in which behavior prediction has kind of spurned the development of end-to-end driving. So there's two, I would say, predominant forms of end-to-end driving. The first is like the very obvious architectural one, right? Like we're going from a cascaded waterfall of components in perception, prediction, planning, control, etc., to just a single neural network, which is, going from sensors, outputting an action. That's one very, let's say immediate form of end-to-end driving. Another one, which I would say is not too obvious, is that even if you have a cascaded set of components, you can couple them in other ways beyond architecturally. One thing you can do is actually couple metrics so that, for example, the way that you evaluate your trajectory predictor is also tied to how well your planning and control is performing. So this is now a way that you can get, information across components, even if you have this kind of cascaded waterfall. And I'm going to actually just start to briefly talk about that idea, or at least one potential idea for doing this. This was a paper from a few years ago, where what we noticed was that in trajectory prediction, you guys have probably studied all these kind of displacement error-based metrics, log likelihood, these kinds of metrics for evaluating performance. The problem with these metrics is that they are agnostic to errors on either side of the ground truth. So if your prediction is a little bit too much to the left or a little bit too much to the right, it's all the same in the eyes of the metric. The problem is in the real world, that's not all the same, right? If your error is putting you closer to a car on the one hand versus the shoulder on the other, one is, a decently dangerous mistake. The other one is annoying, harmless, but pales in comparison to the first error. And so one of the questions we were looking at within this work is how can we actually bring this kind of task agnostic, kind of task awareness into metrics. And, we were looking at a lot of different desiderata, but the main thing that we, wanted to look at was how to capture asymmetries in downstream tasks, but also how to make sure that we do this in a way that doesn't favor, one class of prediction methods or one class of motion planning methods. And then, of course, we wanted it to be pretty easy to compute compute offline and interpretable to practitioners who are using it. So what we came up with in this work was, if we wanted to couple something like trajectory prediction and motion planning, there's a typical interface that you always pass through between the two components, which is the computation of a planning cost function. And the good thing is that a planning cost function basically tells you how good is your plan or not. And what you can do is, with that planning cost function, then you have, you know, tons of different motion planners that can optimize that and get you a good trajectory that actually satisfies this. But before you even have to go to the method, you can use the planning cost function as kind of a tool to measure how good or how much your prediction will affect downstream motion planning. Because if your predictions suddenly cause your motion planning cost to skyrocket, that's going to drastically change what your planner does. Because now your planner really wants to get out of that regime and really wants to do something else, which means you can kind of predict that your planner is going to have a sharp reaction to something like its cost being driven up drastically. And what we did in this work was we exactly wanted to leverage this idea, which is that the planning cost function tells you a lot about what's going to happen. But again, we didn't want to assume that, you know, we didn't want to assume and take some off-the-shelf planning cost function, which means that this method might then just favor, you know, RRT star or something like that as a motion planner. So what we did is we said, okay, let's see if we can learn a reasonable planning cost function from data. And that's where this kind of continuous inverse optimal control block comes in. And then we're going to take this learned planning cost function, and we're going to take its gradient with respect to upstream components. So for example, trajectory prediction. And because then I'm going to be able to basically infer planning sensitivity to that component. So if my trajectory predictions change a little bit and then my planning cost skyrockets, that means I'm really sensitive to that prediction. And when we actually did this, we were able to see, so we looked at two components, trajectory prediction on the right, and then actually even object detection, which is even earlier in the stack on the left. And what we saw was that, you know, we're able to identify detections or predictions for which, even if they're erroneous, they're going to cause a large delta in our planner. And so, for example, when we highlight, like, you know, the kind of maximal changing object detections, we can see here that, like, you know, this kind of, you know, erroneous bicycle here, or this kind of erroneous car here, marked in yellow, basically has the most effect on our planner. And so it means that that error is actually the most effectual to our downstream planning. Same thing we can see here. We can identify which agents, colored basically from blue to red based on sensitivity, we can identify which agents are most impactful to our future motion plan. And here we can see, you know, for these pedestrians which are about to turn onto the road, this specific agent, which is closest to us and about to enter the crosswalk, is going to affect our plan most in the future. So already you can kind of see some interesting, at least from an analysis perspective, you can see some interesting findings. The other thing that the way that you kind of tie this all home is by bringing this notion of planning sensitivity actually into metrics, into evaluation metrics. And so what we did was there was kind of two ways we can do this. You can either change like the actual metric itself to take into account this planning sensitivity, or you can do something like binning your metric based on different values of planning sensitivity. So I'm showing here how kind of we can change precision recall so that you're penalized more if your mistakes happen for an object in which you're really sensitive to that object. And here we can also bin, for example, the ADE of a trajectory predictor based on how important that object is. Just to give you kind of an example of how we can do this for metric coupling. The other end of the other side was architectural end-to-end driving. And, you know, like I said, traditionally, maybe 5 years ago and more, and even still to this day, to be honest, you have this kind of cascaded set of components for autonomous driving. Then on the other hand, you know, and in the spectrum, you have just sensor to control. Now, the problem, you know, there's kind of benefits and drawbacks of both. You know, the chief one for end-to-end architecture is being interpretability. You have potentially no idea what's going on in your network. Whereas in the modular AV architecture, you might be leaving some performance on the table because you might have information bottlenecks between these components. The good thing is you can kind of view these as, you know, forming the ends of a spectrum. And then you may be able to think of, okay, can we have something like a modular architecture, which is differentiable so that it can be trained end to end? And this is kind of, you know, I can kind of tell you the answer is yes ahead of time here. And what we did was, you know, even if the answer is yes, there's still a really big design space that you have to contend with, right? you have to think about, okay, how do we, which modules should I even use, right? Do I need to do, within perception, do I need to do object detection? Do I need to just do bird's eye view, semantic classification? Or, what kind of representation do I need to pass between these kinds of things? Do I just do rasterization? Do I do vectorization, right? All these kinds of questions. And then even if you do choose your modules, how should I even couple them, right? Which module should flow between which other module? And the reason I kind of want to always keep in mind that behavior prediction is really this core component is because behavior prediction is kind of how you translate world static context understanding into something that planning can directly use in the kind of trajectory space. Whereas, when you're, if you just look at these videos, right, we're not looking at any, or at least too many trajectories here if we're just looking at this same context. So prediction is almost kind of like this, one of the key translation layers going from perception to action. Anywho, what we did in order to answer this question in a paper actually earlier this year was we actually built a computational graph framework that allowed us to basically mix and match all these different components, all these different things you might find in perception, different ways of doing prediction, different ways of doing motion planning. And we kind of threw them all together and said, okay, let's basically train tons of different options and see which one comes out to be the best. And what we found, interestingly enough, is that actually a pretty simple architecture ended up performing pretty well. Basically, what we found was that if you take all your sensor observations and any other kind of conditioning information you want, and you embed them into a shared latent space, could be a bird's eye view representation, could be tokens, could be, there's many choices here. And then rather than having, all of your autonomy stack components feeding into one another, they actually now become basically training losses to shape this latent space. And why that's interesting is because what it means is that actually now you enable even entirely different paradigms of executing a kind of stack like this online. Because yes, sure, you probably need to run motion planning every single frame, and you want to make sure that it's excellent and very high fidelity. But do you need to run mapping every single frame? Do you need to run motion prediction every single frame? Do you need to run occupancy prediction every single frame? Or can you skip a frame? Or can you skip 3 frames? Or can you skip 4 frames? And what that means is that you're actually able to save greatly on the computational costs. And here I'm showing a direct comparison. I don't know if, because of the network, you're able to see this easily, but basically the previous state-of-the-art method could run, let's say it's 6 frames per second, whereas this architecture is able to perform at the same level of accuracy, but run 4 times faster. Because again, you don't have to run some of these components online because you can just use them as auxiliary training losses. And here I'm just showing a few more kind of qualitative examples. But since that paper, we've even tried to scale things up a little bit and try some different auxiliary losses, like a little bit more into the realm of foundation models, right? Like maybe we can use video generation as a pre-training task. Maybe we can use, language prediction as a pre-training task. Who knows, right? Like the world is completely open at this point in terms of what you can throw. And yeah, what we did was we actually trained this exact architecture, and we used video generation as a pre-training task, in addition to trajectory prediction, which is absolutely essential in actually moving the car forward. And what we found was that actually these, having a simple architecture like this with relatively simple training losses actually is able to learn driving behavior. And here I'm showing an example of a car driving in simulation. So, it's of course early days for these kinds of stacks, and there's lots of challenges, of course, before you're going to deploy anything like this in the real world. But it's really interesting and really promising, and to see these results even early on. And again, tying it back to behavior prediction, all of this comes because of how essential it is to have future forecasting as a training task, even in addition to whatever else you might throw into the mix. Now, let's talk about applications outside of just actually driving the car itself. One of the, I would say, biggest areas of investment for autonomous driving is actually in simulation. because we don't just want to, develop a stack, then have to deploy it into car and then test it and then get those findings back to developers and then do the whole process again because it's really slow and really resource intensive anyways. You have to have cars, you have to have entire fleets that you keep testing. And so simulation is really promising tool in order to basically do this all just on your developer desktop to see if the change that you're making on the car is actually going to give you the performance or the improvement or the bug fix that you expect. Now, there's been a lot of different simulators designed and proposed over the years, and they have all many different benefits, drawbacks. But the one thing that's typically missing from most simulators is really intelligent other agent behaviors that can react to what the ego vehicle is doing, that can basically mimic human driving on the road. And so one thing that you might imagine is, well, hey, behavior prediction, right? Theoretically, we have a model that's good at like predicting the future of future motion of things. So why don't we try that? So I'm showing here on the left an example of just normal driving recorded from data. And then on the right, I'm going to show an example of a prediction model, just using a prediction model to basically control an agent driving. And as you can see, even like 1 second after driving, it's basically total garbage. So quick question to the class. Why does this happen? Why is our latest and greatest prediction models, state-of-the-art prediction models, total garbage at controlling vehicles in simulation? Any ideas?
It's like the difference between like open loop and closed loop feedback.
That is exactly correct. Prediction models are trained predominantly open loop. You're just reproducing ground truth behavior, but then you have something called accumulation of errors in closed loop because maybe your first prediction is excellent. Maybe you're only 1 centimeter off, perfection off of the ground truth. But then you do this 30 times a second, and now very suddenly you are 1 meter off, 2 meters off, 3 meters off, and then it's total garbage. Yes, that's exactly the reason. And so, exactly as this subtitle here says, is that closed loop decision making actually, we actually have to kind of rethink this whole paradigm, even if we have behavior prediction models. And there's many desiderata that we might have for simulation, right? We want to have realistic behaviors. We want to have multiple diverse behaviors. We want to be able to control these behaviors because, again, we want to test specific things. But there's lots of challenges, right? Just like your colleague pointed out, we have to think differently about how we handle closed loop scenarios compared to just the normal, data set based predictions that we do normally. So one of the things that we did in our group was we actually decoupled the prediction problem for simulation into 2 components. The first is we actually predict where the agent wants to go sometime in the future. That's kind of the first component. And then the lower level of that hierarchy is just connecting the dots, basically between where the agent is now to where it wants to go in the future. And this is really phenomenal for keeping agent behavior stable because it exactly decouples kind of the one biggest source of uncertainty, which is, what is the agent's actual target goal? And then connecting those dots is very, very simple. You don't even need, for example, a trajectory, you don't even need a neural network to do this. You can just use a very simple cubic spline planner or something like that. Now, what's cool is that with this kind of a decoupled approach, we can get lots of interesting human-like behaviors when you train this on a lot of data. And importantly, because there's a little bit of stochasticity that you can also introduce, even from the exact same initial scenario, you can get very many different rollouts. And a common question that comes up is, okay, if we're now in the simulated world, how can I even evaluate the quality of these trajectories? And there's 3 things I want to communicate here to you is that when we kind of step into the world of simulation, there's no ground truth anymore. And so now we have to think differently about how we evaluate accuracy or performance. And so it's kind of, I think, kind of what's emerged in the field since then is there's kind of 3 classes. There's metrics where you just look directly at the rollout, just directly at the trajectory, like, is it off-road? Are you covering many different aspects of the map in multiple runs? How diverse are different trajectories from each other? Then you can also look at statistical differences to real-world data, right? If I collect a histogram of my velocities in simulation and I collect a histogram of velocities in real-world driving, hopefully they're really similar, and I can do something like an Earth mover distance or something like that to compare them. Or you can even try and go all the way, down the research spectrum and try and actually learn like a human likelihood measure. But then there's questions of interpretability for that scenario. Now, like I said, there's a few different desiderata, and we talked about some of these, diversity and fidelity, but controllability is still something that I haven't addressed. And one thing that our group has been looking into recently is actually making it very easy for users to provide specifications for motion generation models. And one of the most intuitive ways that we can do this is to leverage text. And so here I'm showing an example of, if we take an initial scenario, how you can make different edits to that scenario just by providing some prompts. Or you can even fully generate new scenarios just by providing a text prompt. And one of the most, I think, high value ways that you can use this is to try and generate scenarios that definitely happen in the real world, but they're really rare. And so collecting data on them is extremely difficult. And, a very typical example of this is actually crashes. Crashes are very rare to see in logged data, but of course they happen all the time, and we really care about avoiding them. And so here I'm showing you an example of taking some text prompts from a NHTSA database of crashes and actually reconstructing them and then rendering these trajectories and other vehicles in a simulator. Here I'm showing a simulator from NVIDIA. But while this capability is already very impactful, there is still a little bit of annoyance in, language is excellent at providing, general descriptions of things, but it can be really finicky if I want a vehicle at exactly, position with XY coordinates, whatever, or I want exactly this vehicle behind this vehicle at this speed with this distance between them. It can be very cumbersome to kind of keep providing prompts like this. And so one of the advancements on top of this work that we did was basically providing users with the ability to provide actually pinpoint prompts. So rather than just language, you can now also provide goal positions for agents to move to, or sketches for, course trajectory sketches for them to follow, or even discrete actions, like if an agent should stop, turn, accelerate, etc. And, this gives now users a lot of flexibility over how they can author scenarios. And, all of this is really in service of making simulation much more efficient for users to use. And the way that this model actually works, it looks a lot like, what you might see in like a trajectory prediction model that uses transformers, although of course there's now a lot of conditioning information and stuff like this. So the way it works is basically we encode all the scene context, the map, and any initial agent states if you have them. And then we basically, we take all this scene context, and then all of these different prompts, we encode them as tokens into a large transformer model, which can basically attend agent queries to these different prompts, the output of which gives you, it could be trajectories in the case of that first work I showed you, or in the case of this newer work, it gives you these tokens that now represent agent policies. And then you can decode those policies into something that you can actually run in closed loop in a simulator, and which is actually exactly what is going on in this work. So, if you're interested, of course, all the code and everything was literally just open sourced, I think, 2 days ago. So you can find it all at this website if you're interested. And, to say where we're going with all of this is that simulation and having, realistic agents and all of this, the whole point of this is that we want to have, we want to combine. I mean, I know I didn't talk about this today, but there's also a massive line of work in getting sensor simulation really accurate as well. And so where we're working towards this is kind of the holy grail of autonomous vehicle simulation, which is to have very strong sensor and traffic simulation that allows you to do things like this. So here I'm taking a camera log. This is an actual scenario from the Waymo dataset in San Francisco here. And you can see it's a pretty normal driving scenario. This car is approaching a stop sign, and then there's some other car that passes through. But here in the second scenario, we take the exact same one, but we modify something a little bit in order to basically make an otherwise mundane scenario have a potentially safety critical incident. So what you can see here, hopefully the network shows it, is now rather than that car on the left stopping nicely at a stop sign, it actually blows now through the stop sign. And we can render this all very accurately, and we have the trajectories here because, again, we have the simulation model that gives us these trajectories. So, you know, even though this is showing many different, capabilities, I really want to underpin that trajectory prediction is essential for all of this. And so everything that you're learning in this course and everything even we've talked about today, it really all stems from trajectory prediction as this kind of core capability that we need. So to wrap up, I want to share some resources and some takeaways with you guys. So the first thing is that, you know, now more than ever is a fantastic time for AV research. I mean, obviously I'm going to say this because I work in AV research, but, you know, the reason is that, you know, just 5 years ago, there were like barely any data sets, barely any tools or methods that you could use. Whereas now we have like, you know, 10 or 15 data sets that give you an aggregate of, you know, thousands of hours of driving data. The only minor annoyance is that each of them have a, you know, unique format to work with. And so it can be quite annoying if you want to try your method on one, you know, data set and then move it to another. And so I think Karen has actually maybe already described this to you, but in our group, we've actually developed a unified trajectory data format and data loader that actually enables you to use multiple different data sets together, whether you want to, you know, train on one and evaluate it on another, or train with multiple together. It provides a really seamless interface for models. So in case you're interested, you know, I highly recommend looking into this, or in case you're even, you know, doing research of your own in this kind of space, I highly recommend looking into this. And if you're interested in any of the, like those traffic simulation works that I showed, a lot of them have been implemented and can be found within this TB-Sim framework that our group has also released. And I also have a link at the bottom of the slide here. But really, you know, I want to say that I know today we talked about behavior prediction, and I know that you know, I kind of want to make it seem like behavior prediction is kind of the core that underpins everything. But really, just stepping back more broadly, autonomous vehicle research has a lot going on, right? There's safety, there's architectures, there's simulation, there's how can we bring maybe foundation models or other kinds of external advancements into the field. So there's really a lot going on beyond just behavior prediction, even if I think it's a great problem and a great field. So, you know, especially if you're interested, I highly recommend you take a look at our group webpage, or, you know, look into some of the references that I'm showing in these, you know, in the little sublines here under these boxes. So to wrap up, I think the core message is that behavior prediction, even though it's a really simple to state problem, the core ideas and the methods developed apply across the entire AV stack, and even its development just beyond the AV stack. And even though right now we're still developing it, I think closed loop simulation and really accurate closed loop simulation is going to be basically the key to unlocking scale for autonomous vehicles, just like it has for robotics, which you might also be familiar with. And finally, even today there are autonomous vehicles driving around right now, you know, collecting money for commercial trips, there are many open research problems which really necessitate autonomous vehicle research. And so, you know, if you're interested in the field, if you know, I want you to know that now is a really fantastic time to get involved. And of course, you know, where else better to do it than our group? You know, of course, I might be biased, but you know, we are hiring for internships next year for new positions post PhD. So if you are interested, by all means, please apply. And with that, I'm happy to take any questions.
Yeah, any questions in the room?
everyone has a thinking face right now.
I guess I'll start. So if you go back to the slide about simulation agent metrics.
Yep. Let me get back there. I know it's going to stop sharing, but I'll get back there. Yeah. Yeah. What's the...
So yeah, so I think there's like broad categories of metrics. Do you think the ones that have been proposed so far, is that sufficient, or do you think there's gaps currently? Particularly thinking about, these are kind of, again, think about like the lesson of like end-to-end pipelines and thinking of downstream consequences. Like these are all metrics evaluating what the agent does, not how that impacts the outcome of the simulation.
Yeah, no, it's a great point. And actually, yeah, I will say definitely there's gaps. So one is exactly what you just said. I mean, we can evaluate like inter-agent interactions, but broadening your point, we have to be able, so it's going to sound funny, but the biggest limitation is the fact that we have to be able to code it. And okay, that sounds weird to say, but like, how do you code or how do you evaluate good driving? How do you evaluate if driving would be good in Spain versus the US versus Germany versus Indonesia versus Japan versus, right? These things are at some level just subjective. And if we want like hard and fast metrics, like you either collided or you didn't, it's very hard when you start to get to these nuanced scenarios. Or how do you evaluate like the risk that an autonomous vehicle takes or something like that. These are fundamental open problems, not even just in our field, by the way. I mean, this is something you'll see in robotics more broadly, but I would say these are probably the biggest blind spots. And even you don't even have to think that that like far out, right? Like even multi-agent interactions, right? Like imagine coming up with a metric that evaluates if you yielded correctly or if you observed right of way correctly at a four-way stop intersection. That's difficult, right? Like it's you can write hundreds of lines of code to try and evaluate this, or did you stop long enough, or did you stop too long, or was there confusion if your car moved forward? So already in even simple cases like this, there's fundamental gaps in coming up with evaluation metrics. And this, I'm saying all of this because it especially applies for simulation, because these are typically the things you want to evaluate in simulation before you bring them into the real world. So yeah, absolutely, yes.
I have a question about, it's kind of a nitty-gritty question, but at some point in your I forget for which work exactly, but you had the transformer architecture, and at the output you were like tokenizing policies. And I was curious what that, policy tokens, what does that kind of mean in practice? Like what does it mean to tokenize? What's a policy token?
Yeah, so basically, I mean, the paper will have all the details, so if you're interested, by all means, take a peek there. But basically what a policy token in a semantic sense needs to do is it needs to hold all the information that some downstream very lightweight network can take as input, and then know from that information how an agent, basically an agent's kind of class of motion for the next, for the length of the simulation. So for example, if I give a text prompt that says, or if I give like a goal prompt, like agent A has to go to this position, then that policy token for that specific agent basically needs to encode that information that like, okay, in this simulation run, this agent needs to end up there. And so that's like one example of this. Or, if you have a text description, which is like, all agents need to avoid collision, or maybe you say all agents need to collide with each other. I don't know. Then these policy tokens basically need to encode this sentiment and any other like prompt sentiments in a way that like a downstream, very lightweight policy network can take that as input and then basically allow it to condition any future observations and action like generation on that information. So it's kind of like that token acts as the, let's call it the context the lens through which an agent observes and acts on the world. That's like the way I think about it. And if you're interested in like the very detailed, like literally like the literal code or like the literal network that we use to implement this, like I said, this was we just open sourced this maybe 2 days ago, so you can like use this yourself if you're interested.
I have like a clarifying question on the end-to-end architecture. Is it like, because you said that you're kind of combining an end-to-end architecture with a modular setup because it's differentiable throughout the entire architecture, but does every module have its own different network, and then there's kind of like an interplay between the modules, like inputs are being matched outputs? Can you like talk about how that works? And
You are exactly correct. So basically every module here is like, let's call it like an independent component, like an independent nn.module that you might, write in PyTorch. And the only thing that you need to ensure here is that the inputs, the network, and the outputs can maintain gradients, and that you can pass gradients through these different components. So I'll give you like I'll give you an example of like, in perception, maybe you have like a mapping. I'll use like this example here on the right. So maybe you have like a mapping component which like estimates a semantic bird's eye view map of the scene. And so as long as that output, for example, you don't do like an argmax on it, but you maintain, let's say, all the softmax probabilities, then that's actually going to be differentiable. Like you're able to pass gradients from whatever downstream up through that. So exactly. The core essence of a differentiable and modular AV architecture is that you're still going to have like independent components for, for example, object detection or mapping, prediction, motion planning, etc. It just means that the algorithms that you choose for those, or the network architectures that you choose for them, or the operations that you choose with them, they just have to maintain have the ability to maintain gradients, and which basically means that you're not making any argmax, let's say, choices until, for example, maybe the very end, if you need to compute a loss or something like that.
Okay.
Yeah.